We are trying to understand the simplest kind of algebraic extensions that you get by adding just one algebraic element. Like you add one algebraic element. So the setup is that algebraic element has to come from somewhere. So you have an extension k over f, and you take an algebraic element in k. And you consider f round bracket a, which means the subfield of k generated by a over f. And you want to understand the structure of it. In there, you have this subring generated by f and a. So concretely, these are all the rational function expressions using a with coefficients in f, and these are all the polynomial expressions to begin with. Okay. So this is how this discovery went. First, you notice that there is a homomorphism from the polynomial ring to this subring f square bracket a by taking a polynomial to its value at a. So this is basically an evaluation homomorphism, and it's a surjective ring homomorphism. The kernel, you look at the kernel of this homomorphism, the kernel is non-zero, because what is the kernel after all? It's all the polynomials in fx which has a as a root. When you evaluate at a, it has to vanish. So these are all the polynomials in fx that has a as a root, and a is algebraic. So it does satisfy some polynomial. It is root of some polynomial, some non-zero polynomial. So this ideal is a non-zero ideal in a PID. So it's a principal ideal. It has a non-zero generator. How unique is this generator? Well, not exactly unique. You have a freedom, but not much. Any two generator is going to be scalar multiple of each other's. So the only freedom you have is a non-zero element of f. So if I insist that the top degree coefficient is 1, meaning if I insist that the polynomial is monic, then there is going to be just one such polynomial p sub a. So that's what I'm saying here. There's a unique monic polynomial p sub a such that the kernel of this homomorphism is generated by p sub a. And this p sub a is called the minimal polynomial of a. And in fact, it's the unique monic polynomial in fx of the least possible degree that has a as a root. So to give an example, the minimal polynomial of this is x squared minus 2. If you take something more fancy, I don't know, like this, so let's say that's a. So then 2a is root 5 minus 1. So 2a plus 1 is root 5. So 4a squared plus 4a plus 1, if you square both sides, you get 5. And if you subtract 5, you get 4a squared plus 4a minus 4 equals 0. So here is a polynomial with rational coefficients that this number satisfies. It's not monic, so if I divide by 4, I get something monic. So this is p sub ax. It clearly doesn't satisfy anything of degree 1, so this is the lowest degree polynomial that it satisfies. Okay. And then the big thing that we discovered after some discussion is that this field that we want to understand is actually isomorphic to the polynomial ring mod the ideal generated by this minimal polynomial. In fact, it's also equal to f square bracket a. To begin with, we didn't know that, but now after some discussion we discovered that as well. And this isomorphism is really taking a polynomial to a class of a polynomial to the value of any representative at a. And if you take two representatives, G and G prime, which are in the same coset, then G and G prime differ by some multiple of P sub A. So H times P sub A. So if you evaluate these guys at A, you get the same thing, because you'll get H of A times P sub A of A, but this is 0. See? So this map is well defined, and that's the isomorphism. Okay. So that tells you the structure of algebraic extensions obtained by one single algebraic element, namely that they are quotients of the polynomial ring by the ideal generated by the minimal polynomial. And in fact, we know the structure of this field. We have looked at it in detail. As a vector space, this is same as, they can all be represented by polynomials of degree less than d if d is the degree of the minimal polynomial. So let's write that. Let d be the degree of this minimal polynomial, then we have the following. And I can tell you what this isomorphism is as well. It's really sending a low degree polynomial to its coset. So that tells you that this is a d-dimensional vector space over F. So all these are d-dimensional vector spaces. In fact, you know basis. A basis here is just, these are just polynomials of degree less than d. So it's a basis is just monomials of degree d minus 1. So this is a basis here. And if you map that over, it just goes to 1a square to a to the d minus 1. These are the bases here. So F A is a d-dimensional vector space over F with basis 1a up to a to the d minus 1. Indeed, we saw q root 2 is really just all expressions of the form a plus b root 2, a and b in q. So these are the two rational numbers you need to write. You don't need any quadratic anymore, because whenever you get to think of degree, because root 2 square becomes just 2, which is a rational number again. See? So for example, the inverses are already in there. So like this number, square root of 5 minus 1 over 2, satisfies the equation a square plus a minus 1 equals 0. So a times a plus 1 is 1. So a plus 1 is just a inverse. So the inverse is already just a polynomial expression. So that's already in q square bracket a. And now I want to say that all this sort of has a converse. So we started with an algebraic element and described the field that you get by adding it. It's same as taking the polynomial ring and quotienting by this minimal polynomial. Conversely, suppose you start with an irreducible polynomial. Then I want to say there is extension of degree d. Let's say. Then there exists an extension, a finite extension, k over f of degree d, and an element in there such that k is obtained by adding that element, and p is the minimal polynomial of that element. In fact, you can take k equal to that guy, right? And furthermore, such an extension is actually unique. So indeed, if k equals fa and k prime equal to f a prime are two extensions by adding single algebraic elements such that p is the minimal polynomial of both a and a prime, then these extensions are isomorphic extensions. What that means is that there is isomorphism from k to k prime that fixes f pointwise. In fact, you get such an isomorphism by just sending a to a prime. You don't touch f, just send a to a prime. And the proof is written out. I mean, it's really, we have gone through this proof before, but it's important to understand what this is saying. It's saying that if I give you an irreducible polynomial of degree d, then you can go to this extension and then identify f in there in a natural way. This is a degree d extension, and if you, so this is the construction, right? And if you let a be the image of x in there, so this is an element of k, then a square is the image of x square, a square minus 3a is the image of x square minus 3a, etc., because that's basically by definition. So p of a is the coset of p of x, but that's just the ideal itself, which is the zero of the field. So we have found an extension and an element in that extension such that this element satisfies the polynomial p. So you could not solve this polynomial in f, but now you can solve it in k because you sort of made k to have a root of p. So a is a root of px in k. And since p is irreducible, it follows easily, this is an exercise, that it must be the minimal polynomial. Or did I say it was monic? Maybe I should say monic. That's nothing much. Okay. And then it follows that this is same as f square bracket a, which is isomorphic, same as f round bracket a. And it's same as what you get by adding things up to degree d minus 1. Yeah, so 1, a square up to a to the d minus 1 are a basis. So it is an extension of degree d. This is a d-dimensional vector space. This one. Okay. So this discussion is sort of going to be crucial for everything that goes forward. This understands the simplest kind of algebraic extensions.